Hello everyone, here I review assignment 1. So let's get started. We'll start with first question. In this question we have 3 loads, F1, F2 and F3, and the question asks us to find the equivalent of these loads or the resultant force. If we combine these 3 loads, what is the equivalent and its direction? So first step, we need a coordinate system. So it's easier to say that if I have X and Y over here and all these loads are applying at point A, then why don't I choose the X and Y to be, let's say, at this point. So this is X, and let's call this one y-axis. All right. So the next step is to find the components of these loads. This one also is very easy. We start with F1. So the load is 150, the angle is 30 degrees. Easily I can find the component in X and Y. If I do so, let's say this will be I write it over here. This will be 150 cosine 30, and this one will be 150 sine 30. So this one is easy. So let's go to F2. If I look at F2, I notice that I have a little triangle. As I explained during the lecture, sometimes instead of angle, we are provided with basically like a little triangle like that. So let's call this angle alpha. So in this triangle, so I have 3, 4. If I use Pythagoras formula, then this side of triangle would be will be 5, right? So I can write it down over here. So if I need then sine alpha, it is 3 divided by 5, and if I ever need cosine alpha, it is 4 divided by 5, right? In this little triangle, sine alpha is 3 divided by 5, and cosine alpha is 4 divided by 5. So now that I have the angle, what I need to do is simply to find the component for this load. So we repeat the process similar to what we did for F1. So we do it for F2. If I do so, then I ended up with a component in the opposite of X direction, and it will be 100 cosine alpha. Pay attention to the direction, right? So the direction, and in Y is going to be positive, and this one will be, I'm writing down it over here, is going to be 100 sine alpha. So we are done with F2. What about F3? So we need the angle first, right? That shouldn't be difficult. Let's say based on the geometry that I have, I try to make a triangle somehow, somewhere. Let's say if I continue this point, this line along Y, and also this one at point B, so I notice that yes, there is a right triangle over here, right? And in this triangle, luckily I have, let's call this point C. I just quickly draw this triangle or a smaller version of that over here. So in order not to make our basically the diagram messier. So in this triangle, if this is point A, this is B, and this is point C. So this side of triangle is 2 meter, right? If you notice, the whole thing from the wall to the wall is 4 meter, and then from the wall over here is 2 meter, so it leaves me with 2 meter from B to C, and I have 1 meter over here and 3 meter over there, so this one is 4 meter. If I use Pythagoras, then I'll get the square root of 20 basically for the side AB. And similar to what we did for that little triangle over there, let's call this time this angle maybe beta. And if I ever need sine beta, then it's easy. Sine beta is 4 divided by the square root of 20. And if I need cosine beta, then cosine beta is 2 divided by a square root of 20. So let's find the components for this load. So the load is 200 Newton. I find the component in X and in Y direction, right? So this is this parallel line in order to make sure that I don't make a mistake. So let's say this is the angle beta. If this one is beta, so we notice this one also is beta, right? Because these two lines are parallel and we have an oblique line. So if this angle is beta, this angle also is beta. So based on that, we can write down that, well, this force, this one, and I write it down over here, is going to be 200 then cosine beta, and this one is in the opposite direction of y axis, and it will be 200 sine beta. We did almost we almost solved the problem because the rest is just simple adding and subtracting, right? But still we need to be careful not to make mistake. We start with sum of the forces in X. What do we have in X direction, right? In X direction, I have 150 cosine 30. It is in X. I have minus 100 cosine alpha, and I have 200 cosine beta, which is positive. 200 cosine beta. So I have all these things that I need. I have cosine alpha, I have cosine beta. If I substitute them, I will get 139.35 Newton. So as you can see, I kept 2 figures after the decimal point. As a rule of thumb, as I explained in the lecture, we try to keep at least 2 figures after the decimal point. But most of the problems, they ask in your exam, they ask how accurate we want the result. 2 figures after decimal points or more, or it explains. So we do the same in Y direction. In Y direction, we have 150 sine 30. We have plus 100 sine alpha, and we have minus 200 sine beta. If we substitute the number, we get minus 33.86 Newton. So the minus shows that the direction of the resultant force in Y direction is in the opposite direction of Y. In other words, if let me draw the basically this structure again. So the structure is very simple. It's maybe an L-shaped beam. So we have a wall over here, right? This is the wall, and this beam is fixed to the wall. Usually we use this basically schematic to indicate a wall or maybe a fixed portion of a structure. So I have this structure like that, and this is basically point A that we got, right? And also we decided that this to be the X direction and this one to be the Y direction, right? Basically I copied the same picture over here in order not to make it messier. So what we found that sum of all these forces in X is a load. Let me show it like that. This is what we found, Rx 139.35 Newton, and we found Ry to be in opposite direction. So this is Ry, which is minus 43.86 Newton. So if I want the total load, so all I need to do is to find basically the sum of these two loads, or these two vectors, which we learn how to do that, right? So the sum will be basically a load, let's call it R, and this load R, again we can use the Pythagoras formula simply and write it down. R is Rx squared plus Ry squared, and if I substitute these numbers, simply we get 146 Newton, basically the total load. So we found that some of these F1, F2 and F3 is a load which is 146 Newton. The question also asks us to find basically the direction of the load, right? What is the angle of this load? Let's call this angle maybe theta. So it's easy from the geometry we can figure it out. So if I write down tangent of theta is equal to, you see it's equal to 43.86 divided by 139.35. We don't need to write down the negative because we're just solving for the geometry. We have a triangle, right? We know this side. When we know this side, we are curious to find this angle theta. If I do the calculation, I will find out theta to be equal to 17.47 degree. So this is the solution basically to this problem. This is the resultant load, and basically this is the angle or the direction, and also we show it graphically over here. All right, let's solve question number 2. Well, in this question we have a small wrench, or maybe not that small, it's about 20 centimeter, and we are trying to probably fasten this bolt, right? If we apply this load, the whole wrench wants to rotate like clockwise, and so we probably wants to fasten this bolt or not, whatever it is. So the question is asking us to find basically the total moment or torque about the center of these bolt. Let's call this one maybe point O or whatever. So we want to find out M about point O, basically this point, right? So we learned that M, the moment, is equal to force multiplied by the distance, D. Let's call it D. So MO, for example, F multiplied by D. And what is D? We learned that we need to draw the line of action, basically a line that collinear with the force. This is the line of action, and D basically is the distance between point O that we are interested to find the moment to this line. So basically this is the distance d that we are interested to find, right? So we try to find this d, but we notice that we have the horizontal distance, we have the vertical distance. It's not really easy, it's not impossible, but it's not easy to find d. So let me write it down over here. Finding d is not easy, or maybe it is easy for you, you can try later. So but always we try to find this easier solution. So we'd better find a better, maybe we'd better find a better solution. And what is a better solution? Maybe we'd better break basically the load, the force, the 250 Newton into X and Y components, right? So when finding the distance geometrically is not easy, then I suggest you go ahead and break the basically the force to its component. It might make it easier. Let's try together and see how it turns out. So if I try to break this load to its component in X and in Y direction, and always I try to draw the basically the horizontal line, so I avoid making a mistake. Basically what I will have over here is going to be a vertical load and a small, very small horizontal load. So this angle is 15, therefore this small load will be 250 sine 15, and this one will be 250 cosine 15 degree. It doesn't matter if we use this 15 degree or no, if we find like this angle to be 75 and write down 250 cosine 75 and so on. So basically they are the same, right? Now that we break the loads to its component, we notice maybe this time it's easier to find the distance between each of these loads to this point O, right? So let's write it down and see how it turns out. MO. First we start with the easy one, with the 250 cosine 15, this load, this vertical load. So we notice that the vertical distance between point O and this point, right? Again, I emphasize, always draw the line of action. This is the line of action, which is collinear with basically the load. And your goal is to find basically the perpendicular distance, right? The perpendicular distance from this point O to this line of action, this distance, right? Which this distance we know is 200 millimeters. So this distance is 200. It's easy. So MO then it is 250 cosine 15 multiplied by the distance, which is 200. For now, let's keep the units to be in millimeters and the forces to be in Newton. At the end, we can decide for the unit, which unit we want, right? So this is the math. One more step we need to do is the sign. Do we want a positive or a negative sign, right? Is the sign is positive or negative? So as I explained during the lecture, our convention is that the counterclockwise to be positive and clockwise to be negative. So our task is here to figure out if this load trying to rotate this bolt clockwise or counterclockwise. It's easy to visualize it, right? We apply this load. If we apply this load, and let's imagine this is the wrench, if I'm applying this load, so you can notice this load wants to rotate everything basically clockwise, right? So it is negative then. If I apply this load wants to rotate things basically clockwise. So what about the other one? 250 sine 15. So the load is 250 sine 15. What is the distance? Again, we start with the line of action. So this is a small load. If I draw the line of action, this is the line of action. And the distance between this point O and the line of action is this distance, right? Which is basically 30 millimeters. So then the distance is 30 millimeters. So what about the sine? Well, how this load basically wants to, this small load wants to rotate this knot. So if I apply load like that, this load you can imagine more like a car, right? This car is coming, and then it wants to rotate about this roundabout, this point O. So it's rotating it counterclockwise. Therefore, it is positive. So for some, I know it's not easy to visualize it. Maybe it's easier for this load, and because of this long handle that you can visualize, this load can rotate this knot clockwise, but it's difficult for this small load, how it wants to rotate this knot. So you can exaggerate it, that's okay, just to find the right basically direction. For example, if it was me, I would say that, okay, I imagine that I have, like, let's say if this is the knot, I draw it over here. So I would imagine that I have basically a wrench, which this wrench has a very long jaw, basically, like something simple. And instead it has a very short basically arm, right? So in that case, if I apply a load at this point, like this load, like this is the 250 sine 15, this load, so now it's easier to imagine if you apply this load, it's gonna rotate basically this knot counterclockwise. Anyway, it's a matter of practice. You need to practice to find this direction. As you see, it's very simple, but you need to practice to make sure that you don't make a mistake about this sign, because if you make a mistake, then the whole solution is wrong. For now, everything is simple, but as we go further and further, we need to find these numbers basically correctly. So if I do my calculation, I will find out like a big number, 4, 6, 3, 5, 5, and the unit is Newton millimeter for the torque. So I can convert it to basically Newton meter, depends on what the question asks us. In this question, it let us to decide. Maybe it's more appropriate if you use 4, 6, 3, 5 Newton meter, and I approximate it by just 2 figures after the decimal point. Alright, so question 3 is an interesting question. It's easy, but we need to pay attention to the details in order to avoid any mistake. So let's see what we have in this question. We have basically a rod which made out of aluminum and steel. So this portion 3 feet and this portion 4 feet, and then we apply a 2p load at the very end, and then we apply a load p at this end. And so the question is asking us, what is the maximum load that we allow to apply in order that the total elongation of the bar, the total stretch of the bar, because if we apply this load, you know, this 2p wants to stretch basically a steel, this p and plus this 2p, both of them they are applying and they want to stretch aluminum. So we don't want the total elongation, like the amount that the whole things move, exceed the 0.2 inches. So I can first write down that the total elongation, let's call it delta, delta total is equal to the amount that the steel, delta, let's call it steel, plus the amount that this aluminum portion of the bar is extended. And we don't want this total elongation to exceed 0.2 inches. So we want this one to be less or equal to 0.2 inches. So the next step, as I explained in the lecture, is to make sure that all our units are basically in the same basically units. So we look at E is in PSI. PSI stands for pound per inch squared, as I explained during the lecture. And if we follow this unit, then everything, we try to keep everything in the forces in pound and the distance and the length in inches. So the area luckily is in inches square, and 4 feet is equal to basically 48 inches, and this one 36 inches. All right, so that's about the unit. And then we look at these two sections again. As I explained in the lecture, we need to be careful to find out how much is the internal loads basically, right, for each of these sections. So we need to be patient in order to avoid any mistake. And what we do, we imagine that for this aluminum section, if we cut it somewhere, let's say in the middle, somewhere, it doesn't have to be in the middle, somewhere between the end and the start. And if I draw it over here again, let me draw that section again. So I draw it over here. So, and this is where we basically section it, right? Or we cut that portion. So if I apply a load, let's say 2p, whatever load that I have over here, because we are in static, everything has to be in equilibrium, then we know that this 2p causes some internal loads basically over here, right? Which we call them stress. And these internal loads has to balance this 2p. So immediately we notice that these loads, combination of all these load, has to be 2p, right? To cancel out this 2p, otherwise everything starts walking. So then we decide that the internal load for this section is 2p. We do the same for the other section basically. Over here we say if I cut somewhere around here, right, then if again I draw basically where I did the cut, right, so I have basically this portion that I didn't cut, and then I have the aluminum portion, right? This is the aluminum portion where I did the cut. So what I have is a 2p over here, and I also have another load p over there. All right, so we can see we have 2p over here, we have 1p over there. So total, in order to balance these, again we have all these internal stresses or loads. So it means this portion of the bar, the aluminum portion, has to have a load as big as P plus 2P, like 3P, to balance and cancel out this load. So what we've found so far, this is the internal load for steel. So internal load for steel, and this one is the internal load for aluminum. So if we do this portion correctly, the rest is just plug in the numbers and simply we find the answer. So we have the general formula for delta, which is FLA over E. E is module of elasticity, A area, F load, and L is the distance. Let's plug in all these numbers. So the delta for steel will be then, what is the load for the steel portion? It is 2P. What is the length? 48 inches. And what is the area? I have the area over here, 0.4. And also I have E, which is 29 multiplied 10 to power of 6. I do the same for aluminum portion. Delta for aluminum, so the load is 3P, right? We just found the load is 3P. The length is 36 inches. The area is 0.6, and we notice that the module of elasticity for aluminum is less than steel, which makes sense because aluminum is a softer material. So we have delta steel, we have delta aluminum. We plugged in these two delta total, and we simplify this number, we will get 26.27 multiplied then 10 to power of minus 6P. Remember, P is unknown, right? P is unknown. So the question asks us that this delta total to be less or equal to 0.20 inches. So if I simplify that, then I will find out that P has to be less or equal to 76 13.25 pound. So what we found is that the maximum basically load that we are allowed to apply to this bar, the maximum P is 76 13.25 pound, right? If the load exceeds this number, then it means that the whole thing is going to stretch further and it's going to exceed this amount that we are allowed, and maybe the whole structure fail or something happens that we don't want. So it means that this is the maximum load. So a quick review: be careful about first the units, then you need to make sure that you divide basically this bar to two sections and solve each section separately. For each section, again, in order to find the internal loads, try to do a section and see, okay, if the whole thing has to be in balance, what is the internal load? And then the rest is just simple math, and we let the math to do the job. Okay, let's continue with question number 4. Question number 4, we have basically an I-beam. So it's called an I-beam. Later in the chapter for beam, you will see the cross section of this beam is shaped like an eye, so that's why it's called an I-beam. In other words, if somebody stand over here, and let's say if I can draw it, if these are the eyes of a person, then if you look at this area, like the shape of this beam is something like an eye, and that's why we call it an I-beam. But it doesn't matter anyway in this question. So right, this is the view that we see for this beam, and it's called an I-beam. So it says this beam or this I-beam is being welded to a plate, so maybe weld to this plate, and then the whole thing is fastened to the wall. So this is the basically this is the wall, right? And we use 4 bolts and nuts basically. So we can see 2 of them over here. So the other 2 are on the other side of the basically this I-beam, right? So we have total of 4, and the diameter of each is 10 millimeters. This is all the information that we have, and the question asks us to find the basically shear and normal stress, right? Normal stress sigma and shear stress tau in these bolts. And I explained the difference between normal stress and shear stress basically in the class. I'll explain again here. So as I explained in the class, normal stress is when, let's say, my hands, I press them against each other, right? I'm creating a normal stress between my hands. Or let's say if I glue my hands together and I try to basically separate them, right? That's a normal stress. Now, if my hands, I try to slide them on top of each other, basically like that. Imagine again, I glue them together. If I try to slide them on top of each other, that type of stress is called the shear stress, right? So shear stress is always on the surface. We try to slide off something. But normal stress, either we try to pull out something or we try to press something, right? So again, if you don't understand this concept, please go back to the lecture and review them and come back again here. So I can see I have a 30 kilonewton load over here. Again, we can find the component of this load, but first we are allowed to basically say this load, it has its line of action over here, right? In other words, I can say that, well, I have this big load applying to the whole system like that, right? Always remember, when we have a rigid part, we are allowed to basically move the load to the point along its line of action, right? It is its line of action. Then, in order for me to understand the problem better, I prefer to find the component of this load, which again is not difficult. We know how to do that. Let's call this direction X, and let's call this direction to be the Y direction, right? Or the horizontal and vertical directions. So this tau is not for that, this is tau. So, and then what I will do, simply I find the component of this load, which we know how to do that. So the component, always I draw the horizontal and vertical lines, so I don't make a mistake then. So this will be my horizontal load, and this will be the vertical load, right? So this is 30 cosine 40. I have the angle, and this one is 30 sine 40. Now the problem is simple. We notice that this horizontal load try to pull out basically these bolts, these 4 bolts, 2 here, 2 on the other side. It try to pull it out, so it apply basically a normal stress, right? A normal to the surface, while this vertical load 30 sine 40 try to shear off, basically try to slide off or cut off these bolts, so it create a shearing stress, right? So simply I can then write down the normal stress to be the load, but be careful, the load we have 4, we need to divide it to 4, because simply the question said that it's okay to assume that the loads the load is equally divided among these 4 bolts. So we just simply divide it by 4, and then the whole thing's divided by A, right? Sigma is F divided by A. So area P, so we have the load, and then area is pi r squared, which the bolt is 10 millimeters, so it means 5 squared. And I do the same for shearing stress. Shearing stress, as I explained during the lecture, we show it by tau. So similarly, the load is 30 sine 40, right? This load divided by 4 and pi r squared. If I simplify these, I'm gonna get 73.15, 61.38. So by the way, so the force is in Newton, so we need to multiply it by 1000 and also multiply it by 1000, right? So it is in Newton, and the unit for the length is in millimeters, so it means the unit for this guy is going to be in Newton per millimeter square, which simply we call it a megapascal, right? Megapascal is the unit. Again, if you forget the units, go back to the lecture. I explain in the lecture. So this is the normal stress, and this is the shearing stress in these bolts. Question number 5. Civil engineering students usually deal with these sort of problems a lot. So over here we have a wooden pole or column. So this is the wood column, and this wood is sitting on a concrete foundation. So this is the concrete foundation or footing. The question says footing or foundation, and the whole thing is on earth or on soil. And usually again, civil engineering students, they need to deal with this sort of problem. They need to calculate the stresses that the wood create on concrete, and also the stresses that concrete creates on soil, right? So you can think of when you apply this large load, 40 kilonewton load on the wood, this wood try to press the concrete, and the whole things, the concrete try to press soil, and we need to be careful to calculate all the stresses to avoid any failures, right? So the question first asks us to find the stress that wood creates on concrete. So sigma is equal to F divided by A, and the load is simply 40,000 Newton, right? The load divided by the area. So area is simply 120 by 100. So we can keep the units in millimeter, and 120 multiply by 100. It gives us basically 3.33 megapascal. So basically this is stress on the concrete by wood. This is the stress that wood creates on the concrete. So the second part, let's call it sigma or sigma 1. The second part of the question is asking us to find the B, distance B for the concrete. So the stresses on the soil is not exceeding 145 kilopascal, right? It's called the bearing stress. So that's, let's call it sigma 2 is again F divided by A2 of course. So we want the stresses to be, let's keep the units in megapascal. So then it is 145, right? Kilopascal is equal to 0.145 megapascal. So that's the stress. The load is still the same. When we apply this 40, the whole 40 transmit to this concrete and then the whole things to the soil. So 40 transfer to the soil, so right, and A2, which is B multiplied by B, and from here simply we'll find B 525. Again, be careful about the units because this is in megapascal, right? This is in megapascal, this is in Newton. Then it means the denominator has to be in millimeter squared, so it means B is in millimeters. So this is the length of basically B. Very simple. Well, this is the last question, and it's an interesting question. We have here a simple mechanism. Maybe it's a brake mechanism, or maybe other mechanism, but it looks like a more like a brake mechanism, right? So again, it's very important to first understand the question before we start solving it, right? And to understand it, it's better to understand if we are dealing with a mechanism, how it works, right? So let's say if I don't have this this portion, the piston and the rod and everything, right? Like this portion. So I have like an arm like this one over here, which I'm applying a load P 40 Newton, and the whole arms is hinged at point, let's call this point O, basically, right? It's hinged, it's being joined over there. So if I apply this load and there is no rod, so you can imagine this big load 40 Newton can rotate everything, right? Like that. It can rotate everything like that, and the whole thing starts swinging if I don't have the rod, right? But because of this rod and this piston, maybe over here we have oil or gas or maybe some other things, then there's going to be resistance. Basically there's going to be a load over here, let's call this load F, which press against this point, let's call this point maybe A, and it doesn't let basically the whole things to start rotating. Otherwise it wouldn't be a static problem, it would be a dynamic problem if the whole thing starts swinging, right? This load doesn't let. How? Because this load stops the whole things by basically a counter moment about this point O, right? This load wants to swing everything's back counterclockwise, while this load P wants to rotate everything's clockwise. And again, because we are in a static, everything has to be balanced, then we can simply say that this two moment or these two torque has to be equal. So if I draw the line of action for these two loads, so this is for the first one and this is for load F, and this is point O. So from point O, so I can notice that I have all this distance that I want, right? So the moment this 40 Newton it causes around point O, like this big one, we know it has to be 40 multiplied by the arm, right? The total length of the arm, which is 225 plus 50, or 275. And this load F is creating a torque counterclockwise, which this one is load multiplied by the arm or the perpendicular distance, which is 50. So F multiplied by 50, and these two has to be basically balanced. So I simply write down 40 multiplied by 275 has to be equal to F multiplied by 50. Here I don't write the sign because we just care about the amplitude of this load F, and simply from here we can find out the force F, which is going to be 220 Newton, right? So it makes sense when we apply load P over here, which is only 40 Newton, because of this arm, the length and everything, the load that we create in this rod is almost 4 times bigger, right? And now the question asks us to find these stresses in this rod, right? This rod has a diameter of 5 millimeters, and we know stress sigma is F divided by A, and simply A is pi multiplied by R squared, which is 5 millimeters. So don't make a mistake. I usually make a lot of mistake like that in calculation. If we simplify it, we will get 11.20 megapascal. So for now, you may say, well, what's the point of calculating and knowing that the stresses in this rod? Later you will see when we do the design, this number is very critical, because we need to decide what type of material we have to pick for this rod to avoid failure. Because if the stresses, if we pick a material that the strength basically is less than these stresses, then it's gonna fail, right? Or maybe we have to pick a particular material, let's say steel, then we have to work on this diameter. Maybe if the stresses is too much, we simply use maybe a thicker and bigger rod, because the bigger this A, you know, the stresses become less. Or maybe this stresses is too small and we don't want to waste material, so instead of using a 5 millimeter rod, we simply use a thinner rod to save material and make everything lighter, right? But for now we just stick with the calculation. The calculation, as you see, is very simple. Sigma F divided by A. What is F? So from a simple calculation we can find F, but we managed to solve it because we could understand how this mechanism works and how these loads apply, right? Other than that, you see the solution is very, very simple.